copy and paste this into the chat.
Good morning. Good morning.
Good morning.
Okay. So we are talking about how Racket works. Hopefully you guys are playing with it. Are you?
I am whenever I can find time. So namely,
Which means,
this means right now.
Yeah, play with it now. Yeah, not since Monday. Well, that's some though. That's good. Okay, so we talked about lists last time. Let's talk about functions. And as a reminder, this website, Beautiful Racket, I think they have good tutorials. These tutorials, I've not walked through every one of them, but I like these explainers like Booleans and conditionals. They talk about just the basics, and then they go through all the different variations. It turns out Booleans are the tests that you can do. Some of them have some just some interesting applications. You can apply EQ question mark to something, or you can apply equal EQ UAL to question mark to something, and they mean slightly different things. So we have lists they talk all about, right? So that this is better than my notes for sure. Loops, which I'm going to assume are for loops, don't use them, okay? Even though Racket has them, remember that's an imperative device, and so I want you guys to be thinking functionally here, which means use recursion for everything. Okay, there we go, recursion, that's what we want. Okay, so I'm going to be using this once we go through the notes, using Racket and creating composing functions. So in lambda calculus, we would say lambda x plus x1, again, pretending we have numerals in the plus operator in the lambda calculus. That would be how you would define a function. And then when you apply it in lambda calculus, you would say, okay, there's my function, and 7 is my argument. And now I have expression followed by expression, that's application. So 7 basically becomes the input to that function. Functional programs work the same way. You literally use the word lambda and then put your parameters list in parentheses, followed by the expression or the function itself in parentheses. So in lambda calculus, we did this lambda xyz, which was short for lambda x dot, lambda y dot, lambda z dot. Remember, so that's lambda xyz, a function of 3 inputs. And you do the same trick in Racket, the word lambda, followed by, in parentheses, the 3 things that you needed input, and then the function itself. Now it's annoying to have to retype that over and over again. So as usual, you can give it a name. Define, add 1, and then there's my add 1 function. And then when I take add 1 6, notice how that follows the lambda calculus. That's the add 1 function applied to 6. Then I would get 7. Now this form of writing out lambda, the actual word lambda, comes from Lisp and Scheme. Racket does allow you a different way to do it, a different syntactical form, and it's to do it this way: define and then your function name followed by the 2 inputs that you have, all in one parentheses, all in one bracket. I don't care which form you do. I grew up on lambda, so I tend to use that. I like it partly because I'm old, and partly because actually seeing that keyword lambda triggers me, you know, that I'm seeing a function. So if we do lambda, yeah, I should probably do it right. Lambda n, why are you slow? Plus n1, the add one function. Now notice what I'm doing here. All I did is I said, hey, print eval loop, I'm giving you this lambda function, and it comes back and evaluates it and says, hey, you gave me a procedure. Now I have no way of using that, unfortunately, because I didn't give it a name. So struggle with me for a few minutes and then I'll give this thing a name. If I do that followed by 7, can you predict what's going to happen? So I did not put the in parentheses. So what's going to happen is the print eval loop will just say, oh, you gave me 2 separate expressions, but you didn't tell me to do anything with them. I'm going to evaluate the first expression and I'm going to tell you that that's a procedure. I'm going to evaluate the second expression and I'm going to tell you that's 7. So sure enough, procedure 7. What if I actually want to apply the add one function to 7? I have to put it in parentheses. There. Now it's the lambda function applied to 7, and I get 8. Now I'm tired of typing lambda n plus n1, and you're tired of seeing it. Whoops. So let's call it the add one function. And now when I say add one, it says, hey, that's a procedure. And if I say add one, apply it to 5, then it applies to 5. And again, notice the correspondence between this and the lambda calculus. Add 1, 5 is expression followed by expression. That's application. Since the one on the left is a function, a beta reduction occurs and we actually allow 5 to become the input to the function. Language people and functional language people like to use the word operator operand. So basically we have an operator applied to an operand. If you say that long enough, you just shorten it to rater and rand. Now, how do you make more complex functions? Oops, I need n for input. Hopefully I did that right. I did not do, oh. Add syntax multiplier. Oh, because I'm not right. I have to say it's a function of n, and we're adding one to n. There we go, that looks better. Okay, so we get more sophistication by using function composition. That's function composition, right? I'm applying the add one function to the thing that I got when I applied the add one function to n. I find there's a lot of similarities between the object-oriented paradigm and the functional programming paradigm personally. And one of them is that if you're following the object-oriented paradigm faithfully, you have really tiny methods that each do one very specific thing. And so your more sophisticated methods tend to be compositions of smaller methods. Okay. Can you explain how you don't understand it? Oh, let me do it this way. Add 1 to 5, what should I get? 6, right? But what if I add 1 to whatever I got when I added 1 to 5? Well, add 1, 5 is going to be 6, And then I apply add 1 to that. So I get 7. Well, yeah, that's a really procedural way of describing it. It doesn't remember the value, it returns a value. So this thing is saying, hey, take the add 1 function and apply it to whatever this expression is, or whatever this expression evaluates to. And this one is saying, take the add 1 function and apply it to 5, and then it returns a value. So it's returning 6. So ultimately this becomes apply the add 1 function to 6. And it's going to be tricky, but we need to break the thinking of assignment and memory storage and things like that. It's bindings and returned values. So the way functional programming works is not, let's start with procedural. The way we think about how procedural programming works is we have memory and we put something in memory and then we take it out and change it and put it back in, and then we take it out and change it and put it back in. And the way that functional programming works is you don't worry about memory at all. You have values that become inputs to functions, and those functions return values which become inputs to other functions. So what you're doing is flowing values through this chain of functions that you create. And it will take a week or so for you to start to think along those lines. And then it takes, you know, a year of this to feel really comfortable with it. Are you less confused or more confused, Casey? That is progress. Good. I'm going to assume you speak for the group, and unless the group speaks. Okay. So when you start to create, you can see how ugly this syntax is, by the way, all these parentheses. When you start to create functions, I don't recommend that you try to do all the detailed work in one function. I recommend that you make little tiny functions just like you're encouraged to do in the object-oriented world. And then your functions will call other functions. Okay, now let's do something more odd. Nope. That's not good. I keep forgetting to do that part. That's better. So foo is a procedure. Now, what does it take in? The only thing this method foo does, or this function foo does, I'm teaching 225 again, so I keep saying method. The only thing this function foo does is it does application, right? It takes an expression followed by an expression, and if the one on the left is a function, then it will apply that function to the operand. So we have an operator followed by an operand. And I can put in any operator I want, followed by the operand. So for example, I could do foo add 1 to 5, and I get 6. Or I can do foo add 2 to 5 and get 7. I can even do weird things like this. I'm going to make a list. And I can do foo. I think this will work. We'll see. Oh, if I spell it right. So what's happening here? What I'm showing you, by the way, all of these were trivial because I could have just done add 1, 5, right? Add 2, 5, and reverse L1. I could have just done that. But what I'm showing you is the thing that is input to a function. So I have foo is a function. We know that because of lambda, and here's the inputs. The inputs to the functions can actually be other functions. And so what you have is the ability to create these template functions that only differ by an operator and then reuse the template function. And there's an example coming up in the notes. Okay, so yeah, here I'm doing foo operator input. This will really work. Let's do plus 5 times plus 5 2 is 7, right? Times 5 2 is 10. What if I define foo2 to be an operator, an input, and an input? I keep forgetting to do the lambda. An operator, an input, and an input. And then may not work. This may not work. We'll see what happens. I'm missing something. That's that one. That's that one. Why don't I have a one more for lambda? Oh,
I think the parenthesis is wrong.
there we go.
The
there we go. Yep, that's the one. Thank you. So see, what I'm showing you are just simple examples that say, look, the input to your functions aren't just values anymore. There actually can be other functions. So you can create these complex functions that are basically serving as templates, and then all you need to do to have them give you different behavior is tell them what you want to do by putting a different function in there. This is one of the reasons why functional programs can be so short, is because instead of writing out long functions that differ, yeah, well, in this case they do because I'm using the plus sign and I'm using the times, and so they are going to be plus and times are only identified for numbers. But let's think about something for a list. What about append? Should I be able to append 2 lists with this? We'll see, right? The answer is yes, even though I may not have done it right. Ta-da. What about cons? Remember, cons takes in one value followed by a list. So I've created this weird generic function. And so one of the ways that these functional programs can become short, you don't have to write out all the code for a slightly different variation on a function. you just write out 1 and then you feed it the thing you need at any particular point in time. This also has the strange behavior where the code can rewrite itself while it's executing, because you can do if then else's where you're choosing to do this function or that function. It becomes input to the other functions, but that's, you know, way beyond the scope of the course. So the main thing, let's go through the main things here. First of all, do we understand how basic function application works? This is two expressions. The first is the lambda expression, just like we had in the lambda calculus. And then the second is an argument to the lambda expression. And since we have an expression followed by an expression, and the one on the left is a function, then we can do a beta reduction. And basically we're going to substitute 45 for n, and then do the +1 45 operation and get 46. Because no one wants to keep writing that, typing that out all the time, we actually do the definitions. So I defined add1 as a function, and now I can apply that to an argument. Now notice I can't apply add1 to a list. Contract violation. I get a lot of those when I'm programming. And it tells you, I'm expecting a number and you gave me a list. So nice, for the most part, helpful error messages here. So remember when I said that there's good news and bad news with respect to typing in Lisp and Scheme and Racket? The good news is you are not required to declare types. It is not a strictly typed language like Java. And in Java, when you have arrays, every element in the array has to be of the same type, which is restrictive from a programming standpoint, but helpful from a code development standpoint, because it's harder for you to make type errors. Whereas here, the things that you put into a list and the things that you put in arguments, you don't have to specify any type for. And so you have a lot more flexibility as a programmer, but you also have a lot more ability to forget, oh wait, is this a list or is this an atom? You know, you have to keep track of that yourself. And so you have a lot more opportunities to get type errors. Often I hardly get to program anymore. But when I was programming fairly regularly, then the kind of type errors I would get was just, oh wait, I have a list that contains lists and I needed to get an individual atom out of one of those lists. And I screwed up somewhere, and instead of trying to operate on an atom, I operated on a list. By the way, I only made one list so far, right? L1. Who remembers what car encoder does? If I do car L1, what do I get?
Correct me if I'm wrong, but doesn't car return the first element of the list?
Yes, so I should get 3.
Right.
And then if I do cooter of L1, cooter returns the rest of the list, so it's 579. Those of you running Racket at the time, which by the way, wouldn't hurt. You know, you can just do that in real time and answer my questions, right? So what if I wanted to add the first two numbers together, 3 and 5? I have this, I want to add the first two numbers together, 3 and 5. How do I get the first number? And how do I get the second number? It's the car of the cooter, right? If the cooter was 579, then the car of that is 5. So keeping track of these things is going to be challenging at times, you know, when you start to manipulate these lists. So hopefully if I did this right, what do I get? 8? I get 8. How did I get 8? Well, car of L1 is the 3. Notice when you do car of L1, you get 3 back. The list did not change. The list is still 3579. It's just the function car of L1 gave you back, returned the value of 3.
So because the list doesn't change, that's why you have to call the cooter function within
Yes.
R? Okay.
Right, right. It's not like an array where you iterated through and you said, okay, I did the first element and now I equals 1 and I'm at the second element and now I equals 2 and I'm at the third element. It's not like that. The list doesn't change because we didn't, you know, and this is part of breaking your thinking in terms of how memory was working in the imperative and object-oriented worlds. The L1 was bound to 3579, and until we change that binding, L1 is always bound to 3579.
Okay, thank you.
Mm-hmm. So there's a property of these programs that says whenever you see L1, in this case, whenever you see L1, it is always 3579. And you literally can replace the values 3579 where L1 is in this little line of code that I did. So when I talk about thinking about functions flowing values back and forth, this is a small example of it. Cooter of L1 returned a value or flowed a value to the larger expression, and that value is 579. Now we're taking the car of 579, which is giving us the 5. And the car of L1 is 3. And so 3 and 5 were both kind of returned or flowed back to this larger expression of plus 3 and 5. So you're used to thinking linearly, right? Procedurally, step by step. I do this line of code, then this one, then this one, then this one, then this one. And now you need to think of kind of inside out here. Okay, this is a function composed of a function composed of a function. What's happening at that innermost layer? And then what value does it return? Okay, now I'm at this function. What value does it return? By the way, that's annoying to write. So I believe that's the correct shorthand. Yeah, they've created shorthands for these, but you rarely need them. There's also where you can get the nth element. I'd prefer that you don't use that, where you just pluck an element out of the middle of the list by naming its index. That's more of that's more of an imperative and object-oriented way of thinking about arrays, not a functional way of thinking about lists. So I've created another list. I've bound, again, that list 9753 is bound to L2. And I don't know, just for grins, let's make an L3. Whoops. Okay. I listed L1, L2, L3. why did that give me these 3 lists back? Remember, what I gave it was expression, 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 and I did not put them in parentheses. So even though that's an expression followed by an expression, which could be application, if I don't put the parentheses around it, I'm saying evaluate each of these expressions individually and give me these results back. So L1 is 3579 as we had previously defined, L2 is 9753 as we previously defined, and L3 is the 2 appended together. And the only reason I did that is because I want to show you the glorious map function. What map does is applies a function to a list. So in the imperative world, when you had an array, how would you modify every element of the array? You would go through a loop and modify every element of the array. But here, let's see, let's say we wanted to do the add 1 function to every element in L1. So before I did add 1 applied to the car of L1, and I did add 1 applied to the car of the cooter of L1. You know, this is annoying, right? So what I'd rather do if I want to add 1 to everybody is do the map function. And I'm adding 1 to every element of L1. Now, when I type L1, what am I going to get back? Am I going to get back 3579 or 46810? Somebody's furiously trying this, right? Before they answer. The original. Right, 3579. Now, why is that? This is a sharp break between the imperative world and the functional world. In the imperative world, if you walk through an array and you modify all the array elements, you're thinking about it, remember, as, okay, that was stored in memory, I brought it out of memory, I modified it, and I put it back in memory. But that's not what's that's not what's happening here. What's happening here is I said, hey, apply the add 1 function to the list and return a result. And it, sure enough, it returned the result, 46810, but it didn't modify the original list. That's just the result that gets returned when you add 1 to every element of L1. But L1 is unchanged. Just like if I said in the imperative world, think about local and global. No, I don't even want any inputs at all. Okay, after I execute these lines of code, what's the value of y after I call y equals foo? Now we're not in functional world, we're in imperative world now. Yeah, 13. It's 13 because this thing, function foo, says return x plus 1, x is equal to 12, x plus 1 is 13. Now, even though this function returned 13, did it change the value of x? No. And it's a similar thing here. This function, add 1, map add 1 to L1, it added 1 to every element that was in that list and returned that value, but it did not modify the list. In fact, technically in the functional world, once you define L1 to be 3579, it cannot be anything else. It's called single assignment. You're only allowed to give it a value one time. If you wanted to change it, what you actually have to do is define a whole new L1. And this is where one of the parallels to the object-oriented world comes up. If I define an object, if I declare a new object, I get an object in the object-oriented world, right? And then if I said that, oh, I'm on Notepad++. And then I said, object one equals new object of whatever type. And so now I have that object, right? And if I say object one equals new object of whatever type again, what happens to the old object that I created? It's dead, it's gone, right? I've destroyed it and I've created a brand new one. So there's a similar thing that happens here. If I say that I define L1 to be, what was it before, 3579? Whoops. And now I do L1, it's that. The old one is gone. Technically, you can't change these things. You can only create new ones. And again, there's a workaround in Racket because it straddles more than just the functional programming languages, but we're not going to do that. By the way, what does L2 look like? L2 was defined, where did we define it? Way back here, right? Define L2 as the reverse of L1. So L2 is the reverse of L1. So is L2 going to be 9753? Or is it going to be 444333222111100? Another slight change from imperative world. L2 was defined as the reverse of L1. At the time L2 was defined, L1 was 3579. Therefore, L2 was the reverse of the binding that occurred at the time we defined L2. And if we update L1, which really means we destroyed the old one and created a new one, L2 is still bound to the old version. So there's a slight difference again in how you think of, oh wait, surely if I say, you know, in the imperative, oh shoot, I forgot rid of it. In my example previously, okay, if we look at this code, what's the value of y going to be? 13. I think we'll just reuse Lynn's response from before. And then I say x equals 23, and in an imperative and object-oriented world, what's the value of z at that point?
24.
24. What would it be in the functional world?
13.
13, because at the time foo was created, x was bound to 13, x was bound to 12. So every time you run foo, you get 12 plus 1. This is a distinct difference from how functional programming works from how the imperative world and the object-oriented world works. And that's what we're seeing here. That L2 is defined as the reverse of L1, but we have to use the binding that occurred at that time. This is actually a helpful thing You know how sometimes you have to do something with an array, but you want the original array still, so you have to create a temporary new one, and then you mess with the temporary new one. Maybe you have to copy the results back or something like that. You don't have to do that here. You always have the original. Okay, let's get into if then else quickly, and then get into a simple recursive example quickly. And then we'll go through this in more detail on Friday. Okay, if then else. No matter what, I don't care what language you're in. If you're going to do if then else, you need three things. You need a Boolean test. You need something to do if that test is true, something to do if that test is false. All languages have that. So in Java and C, you see it if, parentheses, Boolean test, curly bracket, something to do if it's true, else, curly bracket, something to do if it's false. Here in Racket, in terms of the lambda expression, it's just expression, expression, expression. I have three expressions. The first is the Boolean test. The second is the thing to do if it's true. The third is the thing to do if it's false. Clear all this junk out. If 5 is greater than 3, that's my first expression. That's my second expression and third expression. So my first expression is 5 is greater than 3. Second expression is yes. Third expression is no. Uh-oh. Oh, there we go. It would be good to do the right language. The values £t and £f lowercase. Different languages, different things, right? Some use cat, TURE, FALSE, £t and £f. One of the more interesting tests for a list is it empty? Oh, L1's not defined. This starts to take on more complex shapes, so you want to be careful with how to express those. That becomes a decoding style. I have a note here on equal, EQ question mark, EQV question mark, equal question mark. They're slightly different. You'd want to, you want to read up on the notation. I'm going to just use equal or EQ question mark most of the time. Some apply to lists, some apply to effectively objects that you're creating or functions. Once we have the if then else, we can move into recursion. So let me show you an example. Here's a simple, as you know, factorial is the simplest, the canonical recursive example, right? So if we were going to define factorial as a function, then I'm going to do it still this way. We take an n. I'm not going to check to make sure n is greater than 0. And how do we work with factorial? Let's see. If n is equal to 0, oh man, I don't want this stupid thing. I want this stupid thing. That one. So here's n, and here's n factorial. If n is equal to 0, what's n factorial?
1.
1, right. If n is equal to 2, it's equal to 2, but that's also equal to 2 times, whoops, 2 times 1 factorial. And 3, all the wrong keys, is equal to 3 times 2 factorial. So there's the recursion. So the way to define this thing is to check to see if I'm at 0, and I'm going to check to see if I'm greater than 0. And as long as I'm greater than 0, then I'll do the action, and otherwise I'll just return 1. So if someone wants to sneak in with a negative 1, I'll just return 1. So the way this is structured, there's my empty structure, right? There's my lambda definition. There's my function definition. And that's the whole expression. So define factorial to be whatever I put in here. That's the lambda expression. I need to put my function in here. What's my function? If n is greater than 0. And I like to do this to remind myself, do something else, do something else. Now, what's the thing I do if n is less than 0? I return 1. What do I do if n is not less than 0? If n is greater than 0? Then I return n times factorial on n minus 1. Did I get all that right? I've got it here correctly, so let's make sure I did it correctly. Right, so that's what I'm saying in here. I'm defining factorial n. I did it not the lambda way this time. If n is greater than 0, then you have to take n times factorial of n minus 1. If n is not greater than 0, just return 1. Okay, I've defined this for the first time up in this window up here. I have to hit run, and that sets all of the definitions. And if I do factorial, it says that's a procedure. And if I do factorial of 4, I get 24. Okay, so we've got the if then else in here, and we've also got our first occurrence of recursion. Now here we're recursing on the integer, on the factorial function by incrementing the integer down. So what I'm going to do on Friday, let's have a lecture on Friday, not office hours. On Friday, I'm going to keep talking about this kind of how you create these functions. And you'll see after you see it at the first time, it's like, that is kind of weird. After a couple times, it's very natural. In fact, if hopefully you're looking at these notes, here's a find max. And then I've got this notion of, look at this, these guys are, it's the same pattern over and over again. So once we do this a few times, it's going to be that this pattern shows up over and over. And then it's just a matter of some of the details changing inside the pattern. Okay, but for now, I got to let you guys go. Please play with this stuff. I give you example files in the slides, and that beautiful racket page also gives you lots of good walkthroughs for the individual piece parts. Okay, if you have questions, obviously put them in the discussion.